Hi folks, our goal in this video here is to find an equivalent expression for cos of a minus b. So not surprisingly, this might be something that we might want to rewrite, presumably in terms of a trig ratio of the individual angles here. Okay, now I suppose in the best of all possible worlds, this would be equal to the cosine of A minus the cosine of B. But if you try out one example, you'll see very quickly that that is not true. Okay, so it's a little more complicated than that. And so we're going to spend some time finding an equivalent expression analytically. But what's good about finding an expression of cos A minus B is that using that result, we can then find much more easily an equivalent expression for cos of A plus B. And guess what? We can then use those to find equivalent expressions for sine of A plus B, sine of A minus B, and then tangent. Okay, so the idea here is that we put in some sweat equity into finding our first equivalent expression, but then the other ones follow a lot more easily. Okay, so in order to do that, I'm going to start by revisiting angles on a Cartesian plane. Okay, because I'm going to need this to set up the proof that's going to come soon. Okay, so here we have an angle that's defined on a Cartesian plane, again from the positive x-axis, and we know that we define the trig ratios using the x and y values of any point on the terminal arm, as well as this r value here, which is the distance from 0, 0 to that point on the terminal arm. Okay, so keep in mind it can be any point on this terminal arm. So I'm going to choose points that are all 1 unit away from the origin, okay, that lie on this unit circle. Okay, so I know that this r value, the way I'm choosing my points, has to be equal to 1. But by doing that, we see some nice things happen, because let's take a look at what cos of theta would be. So we know cos of theta is x over r. Okay, so when we write that out, we realize that cos of theta is just equal to x over 1. So in other words, your x value has to be equal to the cosine of the angle. And similarly, if we look at sine theta, which is y over r, well, that's just going to be somewhere here. There we go, y over 1. Okay, in other words, the y value is just going to be equal to sine theta. Okay, so as long as I'm picking my point on the terminal arm such that it lies on this unit circle, okay, the point is always given by cos theta sine theta. Okay, so this is how we're going to start to use that in our problem. Okay, so the way I'm going to set up my proof for cos of A minus B, okay, is I'm going to start with an angle A here, and then I'm going to start with a smaller angle B. Okay, so here's the terminal arm for B, the terminal arm for A. The angle A minus B will be this angle between the two terminal arms, because it's angle A, take away this small angle B. Okay, now given that I've chosen the points on the terminal arm to be on the unit circle, I know that this point here on the terminal arm of B will just be cos B sine B, and the point on the terminal arm of A will just be cos A sine A. And I've joined these two to form a triangle. Okay, so our goal here now is to see if we can find an expression for cosine of A minus B. Okay, and let's see how we can do that. Okay, so we've got our diagram here. Now remember that because these 2 points are on the unit circle, I know that the length of that side of the triangle is 1, and the length of this side of the triangle is also 1. Okay, but let's take a look at what we have. We have 2 side lengths of the triangle, and I'm interested in the angle that joins those 2 sides. Okay, and I'm also interested in discovering the cosine of that angle. Okay, so this really looks like a prime candidate for the cosine law. Okay, so in order to use the cosine law, though, I'm going to need the opposite side to my angle A minus B. Okay, that I'll need for my formula. And since I know what these 2 points are, I actually can determine the length z that I called z here. It's just the distance between these 2 points. Okay, so let's remember what the distance formula is between 2 points. So the distance formula is given by the difference in the x values squared plus the difference in the y values squared and the square root of all that, which of course is an application of Pythagoras. Okay, so let's put in what we have here for z. So I'm looking for z here, and the difference in the x values, well, is just going to be x2 minus x1 is just going to be cos A minus cos B all squared. And then I'm going to add to that the difference in the y values, which is just going to be sine A minus sine B squared. So sine A minus sine B squared. Okay, and now I have all the information I need to apply the cosine law. Okay, so let's remember how the cosine law works. Well, if I take the side opposite to the angle I'm using, okay, that's going to be isolated on the left side, so z squared is going to be equal to the sum of the squares of the two other sides, so 1 squared plus 1 squared minus 2 times the side lengths of those other two sides, so times 1 times 1, times the cosine of the angle opposite z, which of course is going to be A minus B. Okay, so this is the equation I have. Okay, this is the expression I'm trying to isolate because I'm trying to determine another expression for cos of A minus B. But I want you to notice what's going to be input on the left-hand side of the equation. A whole bunch of expressions that contain sine of A alone, sine of B alone, and cos of A and B on their own. Okay, so our goal is to input this in here and hopefully simplify it into a more manageable expression. Okay, so let's go ahead and do this. So I need z squared, so it's just going to be the square of this square root. So that's just going to give me cos A minus cos B squared plus sine A minus sine B squared. Okay. And then on the other side of the equation, I've got 1 squared plus 1 squared, so that's 2 minus 2 times cos of A minus B. Okay, now I just want to remind you here, because this is a really common silly error that people still make sometimes. You can't subtract these 2's because you got that multiplication there. So just in case you were thinking of it, remember you got to follow the order of operations. Okay, so we could now isolate cos of A minus B, and you'd have an expression in terms of the coses and sines of A and B, but it's a pretty ugly expression. Okay, so let's see if we can simplify this. And again, we're going to do a lot of work now, but hopefully to eventually save ourselves a lot of time in the future. Okay, so really the only thing I can do here is actually expand these squares of binomials. Okay, now I don't want to actually write all this out. So on the side, I'm just going to remind us of how we can square a binomial. Okay, remember that x minus y squared is equal to x minus y times x minus y. And if we expand this, we get, well, the first squared. Okay, then we get negative xy minus another xy. So it's going to be minus 2 times these two expressions. Okay, and then negative y times negative y plus the last one squared. Okay, so I'm going to apply this here to these two squares of binomials. Okay, so it's going to be the square of the first, so it's going to be cos squared A minus 2 times the product of the two terms, so cos A cos B, okay, plus the square of the second, so plus cos squared B. Okay, now I'm going to do the same thing with the second one. I'll do this one a little faster. So this will be sine squared A minus 2 sine A sine B plus sine squared B. Okay, and let's not forget our right hand side, 2 minus 2 cos of A minus B. Now, this looks like a total mess up until you realize, well, hey, I've got a cos squared A plus sine squared A. Okay, that's one of our basic identities, and we know that sine squared plus cos squared is equal to 1. So these two simplify to 1. And then I've got a cos squared B and a sine squared B added together, so that's going to be another 1. Okay, so now I'm just left with these two expressions. Now I do notice that they have a common factor of -2, so I'm going to might as well factor that out. So I'm left with cos A cos B. Okay, since I'm factoring out a -2, this is going to be plus sine A sine B. Okay, and on the other side, 2 minus 2 cos A minus B. Okay, but hey, I've got a 2 on the left-hand side and a 2 on the right-hand side. So if I subtract 2 from both sides, there you go. Those disappear. So now I'm left with -2 times cos A cos B plus sine A sine B is equal to -2 cos A minus B. And I see that the coefficient is the same on both sides. So I divide both sides by -2, and all of a sudden I'm left with an expression for cos of A minus B. So cos of A minus B is equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. Okay, not quite as simple as we would have hoped. I mean, remember our first hope was that this was just going to be equal to cos A minus cos B, but it still is an expression, okay, which is relatively simple given in terms of the individual angles. Okay, and this is what we call a compound angle formula because we're finding a new angle by subtracting two other ones. Okay, and what you're going to be doing in class is to use this expression, which took quite a bit of work to determine other compound angle formulas in a much simpler way. And what you might think about between now and then is how this might be useful for us. Okay, so that's it for this one.